Thank you. So good evening. Welcome to the first faculty lecture of the semester. So I'd just like to start out by saying that I'm going to be getting into some organic chemistry and biochemistry, and that's not my area of specialties. But for the last couple of years, I've sort of fallen into teaching some chemistry of forensics courses. And so that's gotten me interested in some of these drug molecules. So I'm going to be focusing on 3 different drug molecules and talking about some of their history and how they've come together to really change the way that human civilization has evolved. So we're going to start out with a quiz. So don't worry. Not graded, but I just wanted to see what you all knew about morphine, nicotine, and caffeine. So, what are some things that these 3 molecules may have in common? I know some of you probably know quite a bit. Alkaloids? So, do you know what alkaloids are, or did you get that from the title? Okay, I'll define that. Just a minute. Ooh. 5. All right, so something from the title. Anything else? All addictive. Okay, all addictive. Yes. So we'll put that next to alkaloids. That's our nitrogen atom. It doesn't have to be chemistry. What? They all have an "ene" ending? Yes, that is that's one I hadn't thought of. Good. Sure, we'll put that up there. Okay, they're from plants. Anything else that you can think of? Do they do anything to? They're drugs? So they affect our bodies in different ways, but they certainly all definitely affect us. Let's put their drugs, I guess. I have a couple others I can add, but
do they do a neurotransmitter thing?
Yes, they're all a little bit different in how they affect the body, but they do affect receptors. Some in the nerve cells and some not. So I don't know how to write that, but they do affect receptors, and that's, yeah, they definitely have that in common. What about toxicity? Do you think they're toxic?
Yep.
So that was kind of a trick question in a way, right? Everything is toxic in the right dosage. Okay, so here's another question. Which one of these do you think is the most toxic? You want to take a guess? You're thinking nicotine? Anyone else think something different? You don't have to comment, that's okay. So keep that in the back. I'm not going to tell you if you're right or wrong yet, but keep that in the back of your mind, because we're going to talk about some of the toxicity of each of these as well. So I do want to go back to alkaloids. So alkaloids are a class of drug molecules that come from plants. So plants goes there. So we'll put plants. And they're basic, so they're alkaline. And the basicity of these comes from them containing a nitrogen atom. And so there's a whole class of drugs under alkaloids, so they come from plants and they're basic drugs. And so these happen to be 3 of them. So here's what I'm going to talk about. I'm going to start with the opiates, so opium, and then from opium, morphine. And you can't talk about the opiates without a little talk on heroin. It has nothing to do with opium wars at all, but it's interesting. So I threw that in there. I'm going to spend the most time on that top piece just because this is a class of drugs that are very well controlled right now. The other 2, nicotine and caffeine, you can get, at least nicotine if you're over 18. So there's some interesting things with the opiates. So I'll talk about those the longest. Then talk about nicotine and caffeine, a little bit about how they work in the body, their history, where they came from, kind of how they've spread throughout the world, and then finally how these 3 molecules came together to really spark the opium wars in China. So that's what we're going to do. Okay, so starting out with the opiates. So morphine is under a class of molecules called the opiates, and they come from the opium poppy. And so here are some pictures of the opium poppy. So I excuse my Latin here, but from Papaver somniferum, which means sleep-inducing poppy in Latin. The Sumerians called it the plant of joy. So they knew about some of the good effects, I guess good effects of the poppy. So there is a picture of the poppy flower. It's actually the immature seed bulb that has this white, sticky latexy material. That's where opium comes from. And it varies between usually 10 to 25% of this is morphine. But there's other molecules in there that have similar effects. So a couple of interesting things that I discovered researching this and finding these pictures. So this picture is from the Vancouver Seed Bank website. Interesting website. They sell poppy seeds, like you can actually buy them and plant them and grow poppies of the opium variety. And they have recipes for opium teas. They also have sold seeds for peyote cacti and marijuana and mushrooms. And so I thought that was kind of interesting, and only one of the, I didn't look at all of them, I was really just looking for this picture, but one of the links to a specific type of marijuana seed said cannot be sold in the US. So apparently the rest can? I don't know, I thought that was kind of interesting. So you can maybe grow your own poppies and have some opium tea. Another interesting thing about the poppy is that the seeds that we eat, poppy seeds, do come from this type of poppy. So if anyone decided to enjoy some of these yummy lemon poppy seed scones, if not, I can pass them around, you can grab one. They actually do contain opiates. Here you go. If you have to take a drug test tomorrow, you might not want to have one, because in fact you can fail a drug test by poppy seeds. But if you don't have to take a drug test tomorrow, there you go, enjoy. So you don't have to take my word for it. I have a little YouTube video that shows this. Mythbusters did this a couple of years ago. That's not the video I'm going to show you. That one's actually probably more scientific, but I'm going to do a Brainiac video from some British guys. I found it more humorous. Okay. I'll show. Sorry.
Who better to find out? Only someone as keen as resident Brainiac prophet, John Tinkle.
Yes, please. I'd like two of your finest bagels, please, with the ones with plenty of poppy seeds on.
It might be hard to believe, but scientific research and American lawsuits suggest that eating the seeds of poppy, the flower from which heroin is made, will produce a positive drugs test. People who eat poppy seed bagels can return results that would even embarrass your average cannabis user. And the theory goes, you only have to eat a couple before your drugs test to return a positive result.
Hi.
Hello, Karen Boswell, I presume.
I am indeed.
I'm John.
Nice to meet you.
Pleasure to meet you.
Would you like to come in?
Of course, thank you.
I've been a judge here actually since but over 1,000 years. Come in, John. Have a seat. You're welcome. We've got some tea. I hope you're into that.
Oh, lovely, yes. I'm dying for a cup.
Good, that's good.
So do note the tea as well. We'll be getting to that.
That's excellent news. I have some bagels here.
Right.
So, if you'd like to tuck into those, shall I be mother and pour the tea?
That would be very kind of you. Thank you.
Excellent.
Yes.
There you go. Dive in.
We want to get loaded.
That's what we're going to do. So how long have you been on the show?
I'm nearly there. Okay.
Okay,
I'll
good.
just get on.
Fine work.
On the tea.
Oh, lovely, thank you.
This is my last piece.
Excellent. Just for added effect, we better get you to eat as many poppy seeds as possible. Would you mind finishing those?
Right. Willingly. Okay.
Superb. Well, I suppose now it's the most important part of the test. I have a little receptacle in this bag.
Right.
I think you can guess what I'm going to ask you to do.
I think I can.
There you go.
Well, I'll go to another room if that's okay.
Okay, please do. Thank you.
sorry to keep you waiting, John, but
That's fine.
there's the sample you need.
Well, thanks very much indeed.
You're welcome.
Now all I have to do is take the sample down to the lab, and we should have the results in about 24 hours. Right then, Cannonballs, I have the results. Would you like to open them?
I would very much, yes.
Excellent.
Yes. Right.
What do we have?
Well, amphetamines, it's negative, cocaine is negative, but I've got to say, opiates, it says presumptive positive.
Oh dear. How do you feel about that?
Well, that's quite worrying, isn't it?
That's an interesting result, yes. And simply from eating poppy seeds.
Well, certainly I didn't take any drugs, I can tell you.
Well, that's good news. Well, there you have it. Unbelievable. Just 2 poppy seed bagels can make you fail the drugs test. Remember, kids, just say no.
Let's see, let me see. Oh, nope, this one. Okay. So I know there's not a whole lot of science in that, but the Mythbusters ones does actually show them doing the analysis, and they also are positive from having poppy seed cake or something like that. So it's true. Okay, so a little bit of the history of the opium poppy. So when you think of the opium poppy, I would always think of something like China, the Golden Triangle, which is down in this area, Burma, Laos, Thailand, kind of over in here. But actually, it originated in the Eastern Mediterranean. So I'm going to have maps for all of the different plants that we're going to talk about, and they're all coming from the National History Museum in London. And their maps are really good. They have a website, Seeds of Trade, where they talk about all sorts of different seeds that have gone all over the world. This one, though, is the only one that I don't really agree with, because they show it almost more originating from Egypt, when really it's more in the Euphrates River Valley, sort of by Jordan and Iran and Iraq, sort of more over here. But certainly it made its way to Egypt fairly early on. So we think up to 5,000 years ago, the Sumerians were using it, and they're around Iraq, Iran area. There are accounts of Egyptians, the Babylonians, the Greeks, so all of the ancient societies that were in this area knew about the effects of this poppy. And so it wasn't until Alexander the Great in 300 BC, when it brought the poppy seed over into India, that it started moving to the east. And then around 700 AD, it made its way to China. And currently, this area is big in heroin production, and we also have this golden crescent up in India that they grow a lot of poppies, and we actually still use the poppy to get morphine, the drug. So, what is in the poppy latex? So I already mentioned that morphine was one of the main components. So it can be anywhere from 0 to 25%. So in this pie chart, it's this little red square, so they have it at 21%. There's other opiates, so other things with similar structures that act similarly to morphine, but are maybe a little bit less effective painkillers and a little bit less addictive. And then certainly there's other things like sugars and water and other things like that. There is one opiate, thebaine, which is an interesting one because it actually is the only opiate that's not a narcotic. It's a stimulant, and so it increases your heart rate, increases nerve firing in your central nervous system, at least naturally occurring. We've made man-made thebaine, and it actually changed the 3D arrangement a tiny bit, and then it was a narcotic. So I'll talk about the structure, don't worry. Those of you who aren't familiar with chemistry, this probably looks like a bunch of squiggles and rings, so I'll talk about exactly what these mean. Okay, so a little close up here. We have morphine and a closely related structure, which is codeine. And these are organic molecules. So when you're talking about drugs that are interacting with the body, you're almost always going to be talking about organic molecules. And all that means is that the backbone is made up of carbon atoms. And our bodies, a lot of things in our bodies are made up of carbon atoms, and so that makes them compatible with each other. And so mostly in these structures we have carbon atoms and hydrogen atoms with a few nitrogens and oxygens thrown in. So you may be wondering, where are all the carbon atoms? Because organic molecules can be quite large, we have ways to simplify their structures a bit, and one of the ways we do that is we don't write out all of the carbons or all of the hydrogens. And so that's where we get all of these squiggly lines. So I'm going to show you where the carbons would go. So at every intersection of a line, there is going to be a carbon. So carbon atom, which is a C, would be there and there. And so every little bend here would have a carbon. And carbon is a nice little predictable atom that likes to have 4 bonds. And so that means that it can attach to 4 other atoms, or it can have a double or a triple bond with another carbon or maybe a different atom. And so we show bonds by just lines in this structure. And so some of our carbons already have 4 things attached. So 1, 2, 3, 4, but some of them only have 3 or maybe even 2. And so in that case, we fill in the missing bonds as hydrogen. So hydrogen just kind of fills in all the extra spots. It is really there, we're not making it up, but hydrogen isn't as important of a piece in the reactivity of these molecules. And so if I was to fill in all the hydrogens, see, so now that carbon has 4 bonds, so 2 single and 1 double, so that double counts as 2. Let's see, we need 1 there. The carbon below actually already has 4, has 2 singles and a double, so that's going to be 4. This one only has 2. And so then I'm going to go around and try to squeeze in all these hydrogens on my codeine molecule. Let's see, let's make sure some of these already have 4. I think that's all of them. Oh, nope, I missed one at the top. There we go. All right, did I miss any others? Where? Oh, there are a few times when we actually do write out carbon. And so typically if it's like sticking off the end of something or if it's an important piece of the molecule, we will write it out. And so this is, I don't know, a medium-sized organic molecule. You can have biomolecules that are carbons and hydrogens that are thousands, if not millions, of atoms big. And so they can get quite large, and we have to figure out different ways to represent them. So you can see how this is a little bit more cluttered, right, when we have all of those different atoms shown. And so we call this a skeletal structure, and it kind of shows the shape of our molecule. So one other thing on here, I don't know if you noticed this part here, where it's kind of a wedge. So this is a 2-dimensional picture of a 3-dimensional molecule. And the way that these molecules are shaped in 3 dimensions is actually very important when you're dealing with things in the body. And so we show wedges as something coming out of the plane at you. So I actually have a model of morphine here. I'll try to line it up here. So the oxygens are red, so there's my OH, there's my ring. The nitrogens are blue. So this is the bond or the ring that's coming out at you. And so you can see there's really quite a lot of structure to this. It's really not flat like it looks on the page. And it's important for some of these molecules to show which way things are facing because when molecules interact with things called receptors in our body, it's almost like a 3-dimensional jigsaw puzzle. And so you have a receptor that has a spot for a certain molecule to come. So just like when you're putting together a jigsaw puzzle, your pieces will fit together if they are supposed to. But once in a while, you can usually shove a piece into a spot that it's not supposed to go. And you can tell that because the colors don't match up, doesn't make any sense. Same thing can happen with these drugs. So they can shove their way up into a receptor that matches pretty closely, but it's not the molecule that it's meant for. And so a lot of these drugs operate that way where they fool the body into thinking that there's something else. And its 3-dimensional structure makes a huge difference. If this ring were pointing backwards instead of forward like that, it may not have any effect on our body. Even just one atom switching direction can change how it affects our body. And this is true for a lot of drugs. All right, and one more thing I wanted to point out. Codeine and morphine are both opiates. So here, let me erase all my carbons here, kind of in the way. They have very similar structures. There's only actually a couple atoms different. Can you tell where they are? Yeah, up at the top. So we have an extra carbon and 2 hydrogens at the top. So hydrogen there, a CH3 group there. Just that small change in the atoms that you have makes a big difference in how they affect the body. Codeine and morphine are both narcotics. Codeine is a little bit less effective of a painkiller, but it's also a little bit less addictive. And so we'll talk now, or I'll go on to talk a little bit about what does that even mean. Okay, so just talking about morphine specifically. It was first isolated in 1803 by a German scientist, Friedrich Serturner, and he named it after Morpheus, the god of dreams, because morphine numbs the senses and makes you sleepy. It took 122 years before they actually were able to figure out that what they had isolated was this. Whoop. So it took a long time to figure out, okay, we have this drug here, it does this, this is what it looks like. But actually, they say that the process of discovering the structure of morphine was as important to chemistry, the field, as morphine has been important to the field of medicine. Because unraveling the structure of morphine really helped scientists or chemists develop new laboratory techniques, new way of doing synthesis, and to really understand the 3D nature of carbon atoms. So they learned a lot of chemistry in the process. So it wasn't just a waste of time in these 122 years. So morphine falls under 2 categories, a narcotic and an analgesic. Analgesic is probably the easiest to describe. It's just a pain reliever. So other common ones are things like aspirin or Tylenol or Motrin. The opiate family in general is a little bit different than the over-the-counter ones because over-counter drugs, they reduce something called prostaglandins at the site of a wound. So like if you cut yourself, your body releases these things called prostaglandins, and they cause inflammation and pain. So say you took some aspirin. What it would do is it would reduce the amount of prostaglandins that your body's producing. So it would relieve some of the inflammation and then relieve some of the pain. The opiates are very different in that they don't do anything local. What they do is they affect how your brain perceives pain. And so that's actually what makes them more addictive. It's messing with your brain rather than just a localized pain relief. And so that kind of takes it into the narcotic area. So to this day, morphine is the most effective pain reliever known. So if you have a major accident, you might be on morphine, or there's some types of cancer that are very painful, and morphine is the only thing that will help. It's been known to be a pain reliever for a long time, and it wasn't that long ago, maybe 100 years or so, that it was freely available. So laudanum was opium in alcohol, and it was often just advertised for women especially. They also had these soothing syrups and cordials for babies. So I looked up some of these ads to see what I could come up with. So there's one. No more dangerous than many of the It's probably true. Back in that day, they had mercury and things and all sorts of toxic things in their tonics. It looked like Mrs. Winslow's was a popular brand. This is from 1887. But this last one is my favorite. I don't know if I can actually believe that this was a real ad, but see what you think. Yeah. So drug your baby, they'll go to sleep. I have to admit, I have a 14-month-old son who is now getting his molars. And, I'm like, I wonder if a few of those poppy seed, I don't know, no, I don't think I'm going to go there. But these cordials actually were up to 10% morphine. And so that's crazy. I just wonder how many babies OD'd or became addicted to it. Ooh. So, yeah. So very addictive. So the more powerful of a pain reliever it is, so morphine is the more addictive it is. And here is toxicity, the legal dose, 200 milligrams. So that's only 0.2 grams. I mean, that's like a tiny little pile of powder. And so this is actually the lethal dose for an average adult. So babies would be much smaller. Okay, so I had to throw in a little bit about heroin just because it's interesting from the forensics perspective and just in general. So heroin was actually made by the makers of aspirin. And so Bayer and Company, the founder was Felix Hoffmann. This was a German dye manufacturing company that kind of accidentally got into drug manufacturing. And before I talk about heroin, I have to go backwards in time 5 years. So Felix Hoffmann had an elderly father who was suffering from rheumatoid arthritis. And to get relief of that, he was taking salicylic acid, which is found in the willow bark. And so this has been known, willow bark had been known for a long time to be a pain reliever. The problem with it is it's very irritating to your stomach. And so Felix decided he was going to try to come up with a way to make it less irritating, but still hopefully keep the pain relieving qualities of it. And so he looked at this group and thought, okay, this group looks like this OH here. It could be reactive, so I'm going to try to change this by doing an acetylation reaction. And so this reaction really isn't that tricky of a reaction. I'm not an organic chemist. I think I could probably still do this one. But basically, you're taking 2 pieces of acetic acid, which is what you smell when you're smelling vinegar, and you take a water out of them, put them together, and make acetic anhydride, and then you pretty much just heat it with that. And so when he did that, he formed acetyl salicylic acid. Don't try to say that 3 times fast, right? And he just replaced this hydrogen here with an acetyl group. And that's a carbon, a double bonded oxygen, and a carbon with 3 hydrogens attached. So he replaced that with this. And lo and behold, it was a better painkiller and it did not irritate the stomach as much. He called it aspirin. Okay, so he made a drug better from its natural derivative. So he thought he would try the same thing with morphine. And so morphine has a drawback of being very addictive, and it also can be irritating to the stomach. And so I'm sure, I don't know if it was just him, he probably had a whole lab of people working on this, but they thought that they would do the same reaction because look, there's these OH groups here. Okay, so we'll react it with acetic anhydride. In this case, instead of just replacing 1 hydrogen with an acetyl group, they replaced 2. And so they formed diacetylmorphine. Which they found out was an even more powerful painkiller, and you only had to take very, very small doses for it to be effective. And so they called this the hero drug, or heroin. And so they did market this as a cough suppressant for emphysema, asthma, relief from migraines. It did not take very long, though, before the dark side of heroin became apparent in that it is very, very addictive. An interesting thing about heroin actually is that in the body, once it gets into our brain, it's actually just converted back into morphine. So it's the same exact effect of morphine. What's different is these groups here allow it to cross the blood-brain barrier more quickly. And so you have a rush of morphine. And so it has a very intense effect. Okay, so what exactly does morphine do in the brain? So I already mentioned that it changes how we perceive pain. So I've been lucky enough to never have to have had any morphine. I don't even know if I've really had many narcotics at all. But I've had some friends who've had accidents and other things, and they say, I remember I could feel the pain, but I didn't care. So it changes your perception of pain, but remember, it doesn't do anything at the actual site of pain. And so there's actually 2 mechanisms they think that account for the properties of all of these opiates, which morphine is one of them. And so one of them is that it can occupy and block a receptor in your brain that endorphins usually, oops, wrong button. Endorphins are usually the go into. So endorphins are natural painkillers that our bodies release in times of stress. And they're big molecules. So morphine is much smaller, but they contain a similar group called the beta-phenylethylamine unit, which is this crazy shape here. So we have a benzene ring, which is 6-membered ring, alternating single double bonds between carbon. The ethyl just means that we have 2 carbons in a line, and then an amine is a nitrogen. And so I'll show you where that is on our model here. Actually, I'll draw it on here first. So on our morphine, there's our ring, there's our 2 carbons, and there's our nitrogen group. So it's kind of on the side here. And so the arrangement of atoms in the 3D structure of this side of the morphine must make it be able to fit into that receptor, even though that's not where it belongs. And so it fools our body into thinking that we've had this rush of endorphins, which can also make us feel good. But they think that there is even another place that they attribute the narcotic effect of morphine, and they call this the morphine rule. So there's 4 components that a molecule has to have to work as a narcotic. Benzene ring, which is the same as before. So here's our benzene ring right here, this ring, alternating bonds. But now, instead of just 2 carbons, we need a quaternary carbon. So that means we need a carbon attached to 4 other things. So instead of going down this way, we're going to go there. So there we have a carbon. Oh wait, sorry, there. There we have a carbon that goes to 4 other carbons. Okay. Then the rest of it is actually pretty similar to the last rule. So we have our benzene group. We go down to this carbon right there. And then we need to have 2 carbons in a line. So we're going to go up here and then end at a nitrogen. And it has to be a tertiary nitrogen. So that means a nitrogen attached to 3 other atoms. And so this effect, we have our morphine atom molecule. So now the first endorphin mimic was kind of on the side. This narcotic effect kind of comes out at you, is this face of the molecule. The way that they actually figured this out is they were doing experiments with Demerol, which is also a narcotic. It's a little less effective, but also less addictive than morphine. And if you notice, look at the 2 structures. They really look nothing alike. They're very different. But Demerol has the same 4 components, where it has the ring, it has a carbon right there that is attached to 4 other things, and then you can go either way around here. 2 carbons and a nitrogen attached to 3 things. The way they found this out was actually interesting. They were injecting rats with these different drugs, and they noticed when they injected a rat with Demerol, it hung its tail in a strange way. And the only other time that they had seen that is when they had injected them with morphine. And so they did some tests on these different narcotics, and that's how they could tell they were having a weird effect on the mice, I guess. And so that came the morphine rule. All right, so that is just a little bit about opiates. There's a lot of information out there, but we have a little bit of time left, so we better move on to nicotine. So tobacco is our main source of nicotine. It was native to the Americas, mainly Central and South America. And the native people at that time had many ways of getting into their body. They could shoot. When they smoked, actually, they tend to smoke out of their nostril, I guess, according to pictures that they've seen. And they also could have like big ceremonial fires and throw the tobacco leaves on the fires and just inhale the smoke as it was coming off. And so these were mainly ceremonial purposes. And they said that it caused trances and hallucinations, which typical smoking cigarettes doesn't do. I don't know, I've never smoked them, but I don't think it does that. But it turns out actually that a lot of the tobacco that was in South America especially was a different strain, so Nicotiana rustica, and it did have more of the active ingredients than the tobacco that's smoked in cigarettes today. So Europeans didn't know about smoking until Christopher Columbus and other explorers came on over and saw the native people smoking, and of course then they brought it back to Europe. There it spread pretty quickly. People liked the way that it made them feel. He did take the other strain. So this is Nicotiana tabacum is the one that's common now, and so it has a little bit less of the active ingredient than the rustica version. And so here's our little map. Okay, so originates in the Americas, makes its way over to Europe, and from there it kind of goes all over. In Europe especially, it spread very quickly. They couldn't keep up with the demand, and so then they started plantations in the New World. And so that has a whole nother host of issues, right, with slavery and, you know, building of an economy in a New World. Not every country approved of smoking, though, and even some Europeans were against it for sure, including the Roman Catholic Church. They were opposed to smoking. In the church, I don't know if they have if they ever allowed that or not. But there were some countries that took it a little bit more extreme. So Russia outlawed it in 1634. Punishment for being caught smoking was they split your lip, I don't know, or castration or exile. I mean, they were taking this pretty seriously, but not as seriously as Turkey, India, or Persia, where you had a death penalty if you were caught smoking. But even with these, it spread all over the world, and people smoke everywhere today. In Russia, the ban only lasted 50 years until Tsar Peter the Great decided he liked smoking, and so he took off the ban. So there are a bunch of alkaloids in tobacco leaves, at least 10. I'm only going to look at nicotine. So you can see nicotine is a much smaller structure, much simpler structure than morphine. And leaves contain anywhere between 2 and 8% of this. It depends on how they're cultivated, where they're grown, how the leaves are dried, things like that. So nicotine works a little bit differently than morphine. It still gets stuck where it doesn't belong. That's kind of a reoccurring theme. But nicotine is interesting. When you have small doses, it can act as a stimulant. It can wake you up, increase your heart rate. But as you get increasing doses, it actually starts to work as a depressant. And so when people want to smoke to relax, it actually can work both ways. So what it does is it imitates a neurotransmitter. And so the nerves that go through your body are just the string of cells called neurons. And they're not connected. They have little gaps in between them. And so you'll have an electrical signal that will follow or fire, and then you have this little gap. And the end of the neuron releases a chemical called a neurotransmitter that floats across the gap, goes into these little receptors, and tells the next nerve to fire. And it just goes down the line. It happens very quickly. I mean, to us, it feels like things are happening instantaneously. What nicotine can do is it can actually go in here and act as a neurotransmitter. So at low concentrations, what happens is our nerves are firing more quickly than they should be, and so it's acting as a stimulant. It's increasing our heart rate, things like that. But eventually, it gets stuck in there, and it actually kind of obstructs the neurons so that they don't fire properly anymore, and so then we have fewer neurons firing, and it depresses our heart rate and things in our body. So it's kind of an interesting molecule. So nicotine is also toxic. Only 50 milligrams can kill an adult in a few minutes. So that's 0.05 grams. That's like a speck. And actually, it's most potent when it's absorbed through the skin. So we have a nicotine container in our stockroom upstairs. I'm like, yeah, nope, I think I'll just leave that one alone. Wear gloves. So nicotine is going to be the most toxic. So you were right. It's made in plants to try to keep away other things from eating it. You can find nicotine in other plants too. Things like tomatoes and eggplant and potatoes all contain a little bit of nicotine. And people used it as an insecticide up until World War II when we had different ones that were available. So very toxic, has lots of effects on the body. When you ingest it, like when you eat it, your stomach acid actually breaks apart most of the active components, so you don't get as much that way. And when you smoke it, luckily the hot temperature of the fire breaks apart a lot of the nicotine as well. If it didn't, it would only take 2 or 3 cigarettes to kill an average adult. So it's pretty toxic. All right, so that's my little tiny thing about nicotine. So now on to caffeine. So of these 3 molecules, caffeine is the easiest to get. It's unregulated. Kids can buy energy drinks that are spiked with all sorts of caffeine. It's found in lots of different plants, and we have it in lots of different beverages typically. And so we'll see that these different plants were found all over the world, and they were known to prehistoric man. We're not really sure which beverage, I guess, was the first enjoyed, if it was tea, coffee, or cocoa, hot chocolate essentially. And so I am going to talk a little bit about these 3 separately. Tea is going to be the one that is important in the Opium Wars, but probably Europe's addiction to caffeine might have been fueled by some of these other ones as well. And so here's the structure of caffeine. Has a few more nitrogens than some of the other things. And we have some related alkaloids, theophylline and theobromine. This one is found more predominantly in tea. And notice it's different only here. Once again, a carbon and 2 hydrogens. This is a little bit less of a stimulant than caffeine. And then theobromine is found in chocolate. This one is also different by a carbon and 2 hydrogens from caffeine. It's over in this spot. And this is even a little bit less of a stimulant, but they still both act as stimulants. Okay, so I'm going to start with tea. Oh, sorry. Actually, I'm going to start by saying what caffeine does in the body. So it's a stimulant, like I already mentioned. It increases heart rate, increases alertness. It has an interesting mechanism, so they're all a little bit different. Still the same idea where the shape, the 3D shape of your molecule is important. And so we have a molecule in our brain called adenosine. Actually, we have it all over our body. It's a neuromodulator, and so what that means is it slows down the firing of neurons in your body. And so it slows you down, and that can make you sleepy. And so what happens is that caffeine can come into those receptors. It must have a close enough fit that it shoves itself into the wrong puzzle piece, right? And it blocks these receptors so that adenosine can't get in there. And so, but the receptors don't respond to caffeine the same way. So it's just kind of blocking the adenosine from getting in there. So basically what happens is you just don't get sleepy. So it doesn't necessarily wake you up, it just prevents you from getting sleepy. However, so we have department meetings at 7 a.m. in the morning, once a month, and that's the only time each month that I drink coffee. And I'm wired that whole morning, I just go crazy. So it does have effects on the rest of your body as well. And so we have adenosine receptors in other parts of our body than just our brain. And so it does the same thing throughout our body, and so that can increase our heart rate. And it causes some blood vessels to open up and some to constrict. It has a variable effect there. But because of some of these effects here, caffeine is actually included in some medications. Things for asthma, it can be a diuretic, so if you have low blood pressure, it can help with migraines, and so some medications do include caffeine. So caffeine is also toxic, but notice 10 grams, that's a lot less than what we had for nicotine or morphine, which is good because I know some coffee drinkers that would probably be dead if this wasn't the case. So here's just a little bean chart, I guess, of how much caffeine is in different drinks. So these are coffees. And so here, Starbucks Grande, 16 ounces, has about 330 milligrams of caffeine. So if you were to overdose on one of those, you would have to drink about 30 cups all at once in order to get that much caffeine. That would be hard, I think. That would be a lot of liquid. So I don't think that's going to be probably happening too easily there. In comparison, we have tea here and some soda. These are the different energy drinks. And then we have some medications like Excedrin, Bareback and Body, Anacin, Xantrex. So different things do contain caffeine. Okay, now on to tea. So I'm going to talk a little tiny bit about tea, coffee, and chocolate, and then how these all come together in the Opium War. So history of tea. Tea originated in China, and the first written account was 200 BC where they knew the effects of caffeine and how it woke you up. But there's legends going back thousands of years of where tea came from. One of the legends says the mystical first emperor of China was boiling his water outside so that the water would be safe to drink, and some leaves fell in it from a nearby shrub. So he drank these leaves and decided that he liked the effects of this drink, and so started tea. Who knows? Who knows if this is true? But it didn't really leave China or the Asian countries until quite late. So 17th century, the Dutch brought it to Europe. It was very expensive at this time because it's pretty rare in Europe, sorry. So only the rich could afford it. But it only took about 100 years for it to catch on and to start to replace beer as the national beverage of England. And so, especially the British love tea, right? When you think, I don't know, when I think of British people, I think of them drinking tea. So keep that in the back of your head. That's going to play a factor in the Opium Wars, how much the British love their tea. Okay, so a little bit about coffee. So coffee originated in Africa, and it migrated its way up to the Arabian Peninsula. And so this area in here became widespread coffee drinkers. And the earliest record here is from an Arabian physician in the 10th century. And so these Islamic countries Middle Eastern countries were drinking coffee for hundreds of years before it made its way to Europe. Didn't make its way to Europe until the 1600s, and again, about 100 years later, it was widespread. Notice this is about the same time frame as tea, so they really arrived about the same time. People started getting addicted to caffeine. They do say, in the book that I was reading, that coffee and tea helped the sobriety of Europe. Before they were drinking beer or wine, breakfast, noon, and night, right? So now, at least breakfast, maybe they can have something different. Okay, and then a little quick thing about chocolate. So cocoa came to Europe actually first, before coffee or tea. This originated in South America, from the cocoa tree. And cocoa, as we now call it, was a bitter drink of the Aztecs. Christopher Columbus actually brought it back with him to Spain, but they didn't realize its utility until Cortez drank it in the court of Montezuma II, and he called it the drink of the gods. It didn't taste very good at that time, I do not believe, but the caffeine effects were apparent. So it comes from the Theobroma tree. There's some seed pods, or beans. And so 1500, so 100 years before tea or coffee made it to Europe, at least the aristocrats in Europe were drinking hot chocolate. So they first started drinking caffeine from chocolate. Okay, so how do these come together? So we have these three molecules. They're all addictive. They all make us feel good, more or less. And so it was really these things in Europe especially that precipitated the events for the Opium Wars. So it starts with opium. So once it made its way to China in 700 AD, it was a respected herb for hundreds of years. You know, it's a great painkiller, and they used it as such. It wasn't until European traders came along and started showing them how to smoke tobacco that things started going poorly with opium. So tobacco arrived. The Chinese government or emperor, whatever it was back then, I guess, banned smoking tobacco, so then Chinese people started smoking opium. They hadn't done it up to that point. When you smoke opium, it's quickly absorbed in your lungs, and you have a very intense effect. It has a very intense effect, and it makes it much more addictive than just eating it as an herbal remedy. So smoking became a widespread problem, a societal problem in China. And so eventually, smoking opium and growing opium poppies was illegal. It was too late, though. There was too much of an underground network, and so opium smoking kept on going, and people in China wanted opium. Okay, so now, so we're missing our third alkaloid, so caffeine. So Europe is now addicted to caffeine. Probably not the worst thing to be addicted to. They like it though, especially tea. And tea back then was mainly from China. And so they wanted to trade with China for tea. China really didn't need anything from the Western countries. They were pretty much, isolated on their own. They said, okay, you can buy it for silver coin, but the British didn't consider that trade. They considered that buying something. So they thought about it and they figured, what's the one thing that Chinese really want? Opium. So Britain got into the opium poppy growing business in India. The East Indian Trading Company was one of the companies that facilitated this. So they grew poppies in India. They went kind of through the back door and through bribed officials, and they got their opium into China, and they got the tea that they wanted. So this didn't go over so well with the Chinese government. And so they confiscated a year's worth of opium in Canton. They burned it, actually. And then a couple days later, a British sailor was killed, and that's pretty much all it took to get this war ignited. And so Britain fought with China for 3 years, and they won. So they were paid back for the opium that was confiscated. China opened some ports to Western trade, but probably the most important thing of the first Opium War was that Hong Kong was ceded as a British colony. And so that's how come Hong Kong ended up being British for until like 5 or 10 years ago. It finally went back to China. So there's another one. 20 years later, France wants to get in the fray and trade with China as well. And so they started another war over little things like a sailboat burning. I think they were just kind of finding things to start a war because they wanted to trade. They wanted to have free trade with China. And so they won. The British, this time it was the British and the French, and they won again. And so this resulted in more ports being opened up to Western countries. This is an interesting result. They allowed Christians to come into the country for the first time, and ultimately it resulted in the free trade of opium. And so it really, these three molecules really changed how China was seen in the world and how they were exposed to other countries. So these three molecules played a large role in this war and, opening up China to trade, but really they've made a lot more changes, a bigger impact on history. If you think about, a lot of these plants were grown in lands far from their origin. In order to do that, they had to clear cut, deforest. In South America, there were slaves that were brought over with the tobacco. So it had a dramatic effect on local populations, not all bad. Some of it drove economies, started countries, made fortunes, but it definitely had an effect on the history of our world. So Napoleon's Buttons was the book that I got a lot of this information from, and I liked this quote, that all of this stuff happened because of our eternal craving for a quick chemical fix. All right, so with that, there's some of my references. Like I said, Napoleon's Buttons, The 17 Molecules That Changed History, is a really interesting book. So this is just 3 of those molecules. And then I got some other random sources. So yeah, I can answer any questions. Thank you for coming.